Lecture 1.3 is the last of the three introductory lectures for the course, and its topic is system performance estimation. The purpose of this lecture is to provide a common vocabulary of different techniques to model the performance of different types of systems, including logistics systems. So it basically provides a set of characteristics of production systems, including logistics systems, that we can use when we want to develop a model. It's a technique for, given a particular design of a system, be able to estimate its different performance characteristics. The first technique for system performance estimation is sort of like guesstimation, sort of the surefire technique. It's a technique called bracketing. And the idea of bracketing is that for many systems, it's relatively easy to estimate the performance of the system if you assume perfect control. So everything operates best case scenario, nothing ever goes wrong, everything is perfectly well operated. Turns out that you can actually characterize the performance of the system under that perfect regime. Of course, no actual system actually ever achieves that level of perfection. At the other extreme, in terms of performance, systems can potentially go to infinity in terms of not performing if things break down. So instead of the theoretical possible infinity in terms of performance, going totally out of whack, it's more effective to look at a situation of what could be termed a practical upper bound or worst case upper bound. And from a systems perspective, that corresponds to the case of no control. If you assume that nothing is being done to actually try to control the system so that it operates effectively, then just like with perfect control, it turns out that there are typically ways of being able to fairly effectively estimate that no control operation. But of course, most systems are controlled, so that provides then an upper bound. So with no control, performance is, much worse than the perfect control, and then the actual performance is somewhere in between. So what we can use then is the notion of the geometric mean that was talked about in the first lecture, 1.1, where we take the square root of the lower bound and upper bound. And that's done in this first example, which is the waiting time for a bus, where you can imagine the case of perfect control. With perfect control, the buses are perfectly separated, so they basically move in lockstep. So a passenger that arrives at a random time at the bus stop would see an average wait of half what the gap between buses are. And then a practical upper bound, assuming the buses aren't controlled at all, the practical waiting time in that case would be a waiting time equal to the headway, which is the gap between the buses. So taking those two values, taking the square root of their product, you can then come up with an estimate of what is the actual waiting time. And again, it basically utilizes two cases that we can solve fairly easily: the perfect control and the no control for the buses. And then the reality is that actual buses operate somewhere in between both of those regimes. Next in the lecture is a discussion of production systems, and the idea here is to give more context to how logistics systems fit in the grander scheme of what can generally be called production systems. The reason to do this is that the techniques of system performance analysis, they may have been developed and first applied to manufacturing or service systems, but those same techniques quite often can be directly applied to logistics systems because the characteristics of all of the systems are actually very similar to each other. Here's a figure that shows sort of a generic production system, and many of these aspects apply to logistics systems as well as manufacturing and service systems. The idea being that the production system itself sees a certain amount of demand, they produce an output, If it's a production system, there's a supply of raw material. And then if things don't work well, there's potentially of having some scrap produced. These are the different production rates that input, and all of these are in units of quantity per unit of time. The first general result for production system is called Little's Law. And for Little's Law, it basically characterizes the relationship between throughput, work in process, and cycle time. And here's a graphic way of describing it. So you have a series of discrete arrivals of, if it's a service system, it would be people to the system. If it's a manufacturing system or logistics system, it could be orders that arrive, and then they're processed, and then they depart the system. So the way of looking at Little's Law is the time between arrival and departure is the cycle time. The throughput is the slope of this line, and then the work in process is the gap along the y-axis between the arrival and the departure. That represents the amount of product that is currently in the system. These are different examples then of the application of Little's Law. And then the next section, section 4 of the lecture, talks about variability and the Poisson process. That's one of the more common assumptions for demand for a production system. A Poisson process is appropriate if you assume that all of the arrivals are independent of each other and that they occur randomly. So with a Poisson process, one way of characterizing variability in general is using a squared coefficient of variation, SCV, and that's C superscript 2. It's defined as the variance divided by the square of t, which is the average time of the process. So with the squared coefficient of variation, you can characterize, it's essentially a normalized variance. And with the squared coefficient of variance, you can characterize different types of variability for a production system. So the case of deterministic, where there's no variability at all, the squared coefficient of variance is 0. In the case of the Poisson process, which is the exponential inter-arrival time, totally random process, the SCV is equal to exactly 1. So that again gives the bound. So like for our bus example, the first case, the perfect control, you would assume zero variability in the separation between buses. So its SCV would be equal to 0. In the case of the no control, that corresponds to the exponential inter-arrival time, or a Poisson process. That would be an SCV equal to 1. So that corresponds to those two extremes. And then most systems are characterized as operating typically somewhere between deterministic and totally random, what's called a moderate variability regime. Again, these are just rough numbers of characterizing the values of SCV to characterize the variability of the system. And then finally, some systems operate actually much greater than 1, and in that case they would be high variability. The next topic covered in the lecture is on throughput feasibility. The idea of throughput feasibility is, given a certain amount of production rate that you want from a production system, and based on and assuming that you have a certain number of machines that are able to process and produce product at a certain rate, you can calculate a minimum number of machines needed to satisfy the demand. And machines is really just a generic term. Don't confuse it with always referring to manufacturing. So in the case of logistics, the machine might be an actual truck. It could be a loading dock at a distribution center. So machine is really meant to be more of a generic, essentially a resource that has a certain capacity. And then these are all of the, in terms of calculating this number, These are all the different parameters. Again, you can read the lecture to define what those are. One of the most important characteristics of the production system is its utilization. And the one strict rule for design and operation of really any type of production system is over a long period of time, a production system cannot operate at 100% utilization. So its utilization has to be strictly less than 1. If it operates at 100% utilization, then anytime there's a disruption, since it's at 100% utilization, there's never actual time to actually make up that lost production. So the queue of material waiting for processing grows exponentially. Here's an example of a 4-line production system. These represent the number of machines, 3, 6, 3, and 2. And here you can characterize some of the performance characteristics of this 4-station production line. Its availability, mean time to failure, etc. The next section talks about, for a particular production system, one of the more important things is to estimate what is its cycle time. Typically, when you're designing a production system, you have an idea of what actual production rate or throughput rate that you want for the system. And then in terms of Little's law, that's only one of the 3 variables in Little's law. And with Little's law, it's essentially a relationship. If you know any 2 of the variables, then you can determine the 3rd one. So if you know the throughput, then you don't know cycle time and you don't know WIP. It turns out that there are quite effective formulas that provide very good estimates of the cycle time of a production system. So given the throughput and given the ability to estimate the cycle time, then you can estimate the work in process of the production system through Little's law. There's various formulas. The most well-known is called the VUT, variability, utilization, and process time form. And it's basically a sum of the time spent queuing or waiting for the production resource plus the time actually being produced. And there's a nice simple formula. This is the case for a single machine, M equal 1. With M equal 1, the variability can be characterized by the sum of the arrival SCV and the processing SCV and divided by 2. And then utilization divided by 1 minus utilization gives the impact of, as you get closer to operating towards 100% utilization, the denominator gets smaller and smaller. So your cycle time really starts to explode. In terms of the variability, if you have a perfectly deterministic arrival process, SCV equal to 0, if your processing time is perfectly deterministic, that's also 0. So 0 plus 0 divided by 2 is 0. That 0 outs this entire term, and the only thing left is the actual processing time. So there's no additional queuing time. So what causes the queuing to occur is to have SCVs greater than 0, and that's the way of estimating what is the queuing component of the cycle time. That same formula can be expanded for more than one machine. So it's a little bit more complicated formula. It has the same basic structure. Here, though, you have M, which represents the number of machines. So that way you can look at what's the impact on change in estimated cycle time by going from 4 to, say, 5 machines. And with that, you can figure out what is that actual impact. Here's a formula that shows what happens to the cycle time as you approach 100% utilization. And what happens is that cycle time increases just very slowly up through 60% utilization, even into the 70, and even as close as 80% utilization. But going from 80 and approaching 100%, you get an exponential increase in utilization. So if you're designing a production system, you want to design it to probably not operate at anything beyond roughly 80%. I mean, sometimes you want to design for more than that, and that's typically because you have a capacity limited resource. that would be too expensive to actually increase its capacity. So then you do what you can to do other factors that can reduce the cycle time, but you're basically having to operate at this higher level. But this is basically the general principle of any kind of long-term design of any type of production system. Never design for 100% utilization. It's just not going to be feasible. Example 5 talks about the pizza delivery time. The same problem was example 4 in lecture 1.1. Here we actually estimate what is the actual delivery time. Now that we can estimate the performance of the system, in addition to just in lecture 1.1, we were estimating what was the average distance for a delivery. Here we're actually estimating what is the waiting time and queuing, including the time waiting for a driver to be available to actually make the pizza delivery. And here you can see going from 4 drivers, which is a 20-minute wait, where the queue time is actually half of the total time. As soon as you add one additional driver, it drops from 20 down to 12. So that's a very significant drop. The next section of the lecture is level 3 simulation. That's one of the levels of modeling. And with simulation, it basically handles situations where we can't use any of the analytical approximation formulas to estimate cycle time. So there are situations where that's not feasible. So the only option is to actually do a simulation. And the good news is that since we're using Julia, doing a simulation is actually very feasible, even for large-scale systems. And that's something that would not be true if you were trying to use like Python to do a simulation. You would have to probably use a simulation package just because Python by itself is so slow that it's really not feasible. The nice thing about Julia is we can do everything in Julia and we get a result that is as fast as you would ever want it to be fast. This is an example of Monte Carlo simulation where we're simulating Poisson arrivals. And with this Poisson arrivals, we get these 2 performance characteristics. We can also do a discrete event simulation. This is a single server queue simulation. And here we're going to assume first in, first out queue simulation. So this is essentially modeling the same regime as the cycle time estimation formula that we had talked about previously, but this is using a simulation to get the actual number. So when this simulation is actually executed, if we run the simulation one time, we know based on the formula that the long run average cycle time should be 0.5. Well, when we run the simulation one time, we get an estimate of 0.53, which is close to 0.5. But because it's a stochastic process, the better approach is actually and this shows the evolution of cycle time as we look at the number of replications in the simulation. Starts off with a lot of variation and then it approaches the 0.5. We can compare a experiment where we do 20 replications of the simulation. And when we do that, we get a result that is much closer to the 0.5. So this essentially is one way of validating that analytical formula. And I know myself, the first time I actually saw that analytical approximation, I thought, well, how good is this? Do I really trust it or not? So I remember sitting down, and in that case I was using MATLAB. I remember sitting down and actually writing this type of simulation and actually doing a simulation experiment. And that was what then convinced me that, hey, that analytical formula is actually pretty good. It's not just a really, really rough approximation. It's actually a really good approximation. And the nice thing about a simulation is that the formula approximation of cycle time basically required that the discipline for the queue be first in, first out. One advantage of utilizing simulation is that we're not restricted. We can actually use other disciplines. So say you have a production system where you always want to process the job that requires the least amount of processing time. In that case, we can have a shortest processing time queue discipline. And the nice thing then about a simulation is it's relatively easy to just then modify the simulation, make some changes to it. We can then run it, see the result, and compared to the first in, first out, where the average was 0.5, if we always pick the shortest processing time to process next, the average cycle time reduces down to 0.29. So we get a big reduction in cycle time by changing the queue discipline. But the real advantage is that making that type of change is really impossible. There's no analytical technique that actually gives us an approximation for shortest processing time. It literally only works for first in, first out. So one nice feature of having simulation in our toolkit of techniques is that in these situations, we can go ahead and actually use a simulation to model exactly what is our system. We don't need to actually compromise. And then finally, it talks about the notion of stationarity. In terms of the formula approximations of the cycle time, they only work when we have what's called a stationary process. That just means that it doesn't have characteristics like this process. Here's a case where when we first start operations, we have a big increase in value, and then it kind of settles down, but there's an increasing trend. So you can take data and you can actually make it stationary by first getting rid of the initial spike in demand. So here it cuts off the beginning, but then it still has this trend in it. You can detrend it by removing the increase, so you get a detrended line. And then finally, there's some seasonality here, and you can then remove the seasonality. And when you finish doing all of it, you end up just with the random demand. The important thing in all four of these figures is to look at the y-axis. Here you start from below 0 up to 20. And then with the trim data, it's between 15 and minus 2.5. When you do the detrending, now it ranges between 4 and minus 6. And then finally, removing the seasonality, the range now is just between 2 and minus 2. So you're basically zooming in, so you have much less variance in the actual data. That's an important assumption to be able to use the analytical formula. The good news is also then for simulation doesn't really have that characteristic. With a simulation, you don't have to require that the data be stationary. And for some production systems, particularly service operations, they maybe never actually reach any type of long-term stationarity. Like imagine like a service shop. They start off in the morning and there's nobody in the shop, so there's no queue. So they start off at 0, and only if they operate for, this is an example for a barber shop. Starting at 0 utilization, this is the increase in average cycle time for waiting at the barber shop. So starting off, there's essentially no waiting, and at 10 hours of operation, the waiting time is only going up to 0.3. But to be able to use the analytical formula for it, it assumes long-run stationarity, and that occurs above 0.4, but it takes over 1,000 hours to actually reach that level. So using that analytical formula is totally not appropriate. But in this case, we can do a simulation where it doesn't matter how long we run it. We run it for 10 hours, which would correspond to the hours per day that a barbershop is open. So that's the basic idea of this ability to be able to calculate performance analysis. And just quick